Hi guys, welcome back to the Biomechanics 1 video series looking at one-dimensional motion, part 3, where we're continuing our analysis with velocity. Now we're going to be looking at some graphical analysis of velocity and what it tends to mean when we look at graphs of position versus time and how it tends to change and what are the implications of that with regards to velocity. Assessing and analyzing those graphs to make more meaningful inferences of what is happening with one-dimensional motion. Okay, so we've established and picked up that velocity, by definition, is equal to the change in position divided by some change in time. What ends up happening is the fact that velocity is the slope, or can be determined from the slope, of a position versus time graph. And I'll show you how that tends to apply in a second, right? If you guys remember from your high school days, hopefully, that when you have a graph, and we'll keep it relatively straightforward at this point in time, that was a linear graph, right? How would I calculate the slope of a graph? That's the question. So between two specific points of interest, this slope over here would be defined as follows. Slope is typically the rise of that graph divided by the run. Some of you might remember it as the change in y divided by the change in x, right? I prefer this method over here versus this one because of the fact that what we call our x and our y axis will change every single time when we look at different graphs, right? So I want you guys to kind of get used to the fact that you're not going to be labeling this x and y anymore. Go by the fact that the slope is a change in vertical divided by horizontal. In this case, our position will be on the vertical axis, and position in one-dimensional motion is just motion along what we traditionally call our x-axis, right? It's just motion in the x-plane. So it's one of the reasons why all of a sudden our y-axis kind of becomes our x-axis, and that might confuse a lot of people, but just think of this x value being representative of position. And then our traditional x-axis is labeled time, right? We'll give it a value of t for time. So this rise of a run is going to give us our value for the slope. So let's assume, as we did in the previous example, that I was moving from some initial position over here, right, and I was moving to the right, and I just keep taking time intervals. So where am I at 1 second, 2 seconds, 3 seconds, and 4 seconds, and we assume that I kind of just keep it, the pace that I'm walking at, relatively consistent. So if I had to just kind of unpack that a little bit, let's say example, at 1 second I was at the 5 meter mark, and then at 2 seconds I was at the 10 meter mark, then at 3 seconds I was at the 15 meter mark, and here at 4 seconds I was at the 20 meter mark. Alright, so what does this mean in terms of my slope, right? I want to try and work out what the slope is of this specific graph. So in this case, my slope, using our new convention, is this change in x, a change in the vertical axis divided by the change in my horizontal axis, which is my change in t. Well, this should start ringing some bells. Alright, doesn't it look somewhat familiar that this slope of a position versus time graph, this change in x over change in t, is exactly the same as what I see when I look at my average velocity. And that's exactly what I was referring to earlier, that the slope of a position time graph gives me my velocity at that specific point, right? That's a really important finding. So what you'll see is, if I wanted to calculate the slope between these 2 points, or let's actually say the velocity at these 2 points, I can find the velocity by simply calculating the slope between those 2 points, right? This change in x over change in t, well, by our definition, delta x is some final position minus some initial position, right? Over some final time minus some initial time. So if I moved forward in time at 2 seconds, I would say that's my final time, and 1 second earlier was my initial time. Where was I between those 2 points? So at the final interval between the 2 places of interest, I was at the 10 meter mark, and just before that I was at the 5 meter mark. And the time that's elapsed was the 2 seconds minus the 1 second. Right, so I'm sitting with 5 over 1, giving me a velocity of 5 meters per second. That's at that first interval. If I look at some other secondary interval, let's say a little bit later, this was 0.1, here's 0.2. Again, I wanted to find out what the average velocity was here. Again, it's my delta x over my delta t, some final minus initial position minus some final minus initial time. Well, in this case, now I'm a little bit further ahead. That's my final position, that's my initial position in this specific time frame, meaning that I was at the 15 meter mark, and just before then I was at the 10 meter mark. The change in time again was 1 second, as it was 3 minus 2 seconds, giving me 5 over 1 and 5 meters per second. I'll do 1/3 one just for fun, just to prove a point that in between this zone over here, my average velocity was also again the slope at that point. Again, look at what my final position was relative to some initial position within that zone. Final time minus initial time. Well, at this 4 second mark, that's my final, this is my initial. Where was I? 20 meters minus 15 meters within that specific time frame, and 4 seconds minus 3 seconds. You can see where I'm going with this. 5 meters per second was my velocity the whole time. You'll notice that all these values are positive. What do we know about positive velocity values? It probably means that the whole time I was moving to the right. And since we're using the example from earlier, we know that that's exactly what was true the whole time. I kept moving in this direction, right? I never turned around or came back or whatever the case may be. Okay, so that's another important distinction. The sign associated with my velocity value will tell me some important information about my direction of movement. Okay, so when I'm dealing with position versus time graphs, if I have a slope that is upwards and to the right, I will have some positive velocity value. If I have a slope that was going down and to the right, I would have some negative velocity value. And if my position versus time graph was level, I would have a slope of 0, right? That might seem confusing, so let me just kind of draw that out here. If I had a position versus time graph, well, let's say at 1 second I was at the 5 meter mark and I kind of just chilled out there, and then at 2 seconds you kind of wanted to see where I was, and I was still at the 5 meter mark, and at 3 seconds I was still at the 5 meter mark. What does that mean? That means, technically speaking, I didn't move, because the whole time, every time that you looked up as a second has elapsed, I was still at 5 meters, right? So if I took the slope of this, it would be 0. meters per second. Makes sense. If I didn't move, I couldn't have had any velocity. Okay, so that's an important distinction that tends to come out of that analysis. Alright, I'm going to apply this to another concept test question, which is going to test your understanding a little bit more. In this case, I also have a position versus time graph. In this case, though, the position is a curved graph instead of a straight line graph. It represents a train cart moving along a train track. It shows the position as a function of time, right? This graph shows that the train is either speeding up all the time, slowing down all the time, speeding up part of the time and slowing down part of the time, moving at constant velocity, or none of these. Again, I would encourage you guys to try and solve this by yourself, see what you come up with, and compare your answer to the one that I will state in a second. Okay, I'm assuming you guys gave that a go, and the answer that you should have come up with is B. Okay, it's slowing down all the time. How did I come up with that answer? Might be a little bit unfair because we haven't really covered it yet, but the principle is exactly the same, right? We're dealing with slopes, and even if it's a slope of a curve, the principle still applies. Okay, the slope of a position versus time graph gives me the velocity, so I'm just going to redraw this graph here. Okay, so if I was interested as the velocity at a distinct point in time, right? If I had to draw the slope at that specific point in time, I'd be guaranteed of pretty much finding the velocity at that point in time. So I'm going to try and just draw the slope that touches that point barely. And if I had to zoom in on this like a bazillion times, I would get a pretty clear picture of what's going on. So if I had to zoom in on this section over here, like really magnify it a lot, what you would ultimately find is that even though it's a curved graph, by zooming in enough, even a curved graph becomes a straight line. And we already know how to find the slope of a straight line, right? It's still this rise divided by the run, or this delta x divided by delta t phenomenon, right? So by zooming in close enough where this kind of tangent line touches this curve at one point, I would be able to find out what the velocity is at that specific point in time. And this is now bringing me into the realms of instantaneous velocity, right? A person would unpack this a lot more in calculus, but in essence, all it is dealing with is saying that the velocity at some instant in time is equal to this change in x over change in t, or this delta x over delta t, as the delta t becomes infinitely small. It tends to approach 0. Remember, delta t is this section here. So as it becomes smaller and smaller and smaller and smaller, to find out what the velocity was at this point in time, which coincides with this point, this delta t becomes smaller and smaller and smaller and smaller, and approaches 0, but never quite gets to 0. And as it's doing that, we just call it a new term, where we say it is dx dt, which is calculus terms for infinitesimally small, right? And we can get some really, really accurate data out of that. But again, it's still boiling down to this whole slope principle. So, a really important distinction, therefore, is the slope of a line that is zoomed at the zoomed curve the same as a tangent line. Is the same as the tangent line at the point of interest. Right, that's kind of what we've just shown. So to see what's happening at the in terms of the velocity at various points on the curve, simply check the slope at various points in time. Okay, so if we had to apply that kind of principle, let me just try and get it some color here. So for example, if I wanted to see what's happening earlier in terms of this train, if I had to just draw the slope, you'll find out it's quite steep. And if I wanted to draw the slope at this point in time, you'll find it's not quite as steep. And then we've already established what the slope is here, it tends to be even less steep. And then the slope at this point in time, where it's just barely touching, it's even less steep, and here even less steep. So the steepness of the curve tells me how big that velocity value is. It's getting less and less and less steep, which means the velocity tends to be decreasing. In other words, it tends to be slowing down all the time. Okay, let's take that a step further. Train moves along a straight track and its position versus time looks as follows. Okay, which of the graphs A, B, C, or D depicts the train's velocity versus time graph? Okay, give that a bash and see what you come up with, and I'll go through the answer in a second. Okay, the answer that you should have gotten is D. Again, if we just apply this principle of this slope, you'll see it's increasing, 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 decreasing, decreasing, and at the top it's 0, right? What you'll find is between this region and this region here, it's relatively consistent. If I had to zoom in, you'll find it's a relatively straight line. The slope of a straight line is a constant velocity. Then it tends to decrease, become negative, decrease more steep. Again, this is a relatively straight line, which means there's again assumed to be constant velocity here, becomes less steep, and 0 again. And that's exactly the type of picture that we see within this graph. I'll unpack the other graph shapes in a separate video. I just want to go through the last section and see what we get there. Okay, here we have two trains. The graph shows the position versus time graph of two trains running on parallel tracks. Train A, which is a relatively straight line, and train B, which has the same kind of curved line. Which of the following statements is true? At time tc, so that's just the time over here, both trains have the same velocity, both trains tend to speed up all the time, both trains have the same velocity at some time before tc, at some time both trains have the same acceleration, or none of these. Okay, so pause the video, try and figure it out, see which one of those statements is true, and we'll take it from there. Okay, so your correct answer should have been that option C, both trains have the same velocity at some time before C. Again, the way in which I would prove that is to say the slope here is some constant value for train A. So there must be some point in time where the slope on B matches the slope on A. And you'll find, it doesn't really matter where it is, but if I had to take the slope, this and this would be equal. It occurs prior to time tc, meaning that both trains have the same velocity at some time before this tc. It's not A. A says that both trains have the same velocity at tc. Well, you can see that the slope of A is significantly steeper than the slope of B at that point in time, meaning that train A has a higher velocity than B. Not that one. both trains speed up all the time. Well, we know that train A is constant because its slope is not changing, and train B has a decreasing velocity as per our previous graph, so it cannot be a wrong one. At some point in time, both trains have the same acceleration. Well, we haven't covered that yet, but acceleration would mean the same rate of change of velocity, which is also not true, because velocity here is constant, velocity here is decreasing, which means they would have different accelerations. And it's definitely not E. Okay, so it's definitely option C. Hope that makes sense. We'll unpack it during class and during lectures some more. So if you have any questions, please don't hesitate to contact me. That's it for the one-dimensional motion analysis for now. We'll have lots of examples. Go through the biomechanics manual. There'll be lots of practice problems for you guys to work on. Okay, see you guys in class. Bye.